Okay, let's start. So, as we're just picking up from last time, we're going to do some more examples on partial fractions because, among other reasons, you have a quiz tomorrow on that. So as I said, tomorrow's going to be sort of a weird day. You're going to do 2 quizzes at once. So you will have the entire section for that. So there's the quiz that you would have gotten on the snow day, which is going to be on integration by parts, trig integrals, trig substitution. And then there's going to be a second quiz, which is shorter, but it's going to be a quiz nonetheless on partial fractions. So I told the instructor to give you both quizzes at the same time. You take the whole time and you finish them in any order you want. But we're going to continue with partial fractions. So I believe 1 over x squared minus 5x plus 6 we actually did, as well as the 5x squared plus 20x plus 6 over x cubed plus 2x squared plus that. So I believe we did this, right? And 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x. We also did that. Did I write this one down? Radical x over x minus 4. Integral of e to the x over e to the 2x plus 1 times e to the x minus 1. We did this one with trig sub before, but now we're going to try to do another version. And if we get through all of those, I have 2 more examples of something that might look like partial fractions, but it actually isn't. But let's get through these so we know we're on solid footing for tomorrow. So did we do this? No, right? So let's do that one. So just find the partial fractions here, and I want you to compute these integrals. That's the goal. So let's move on to the 2x cubed minus 4x minus 8. Okay, what's the first step? Yeah?
You can factor another x out of that first bottom of 1.
Okay.
Well, first we would notice that the power on the bottom is totally bigger than
Right, so the power on the bottom is x to the 4th, the power on top is x cubed, so we don't have to do any long division or anything crazy like that, so we just jump right into making sure that the denominator is fully factored. We can't factor the sum of squares over the real number, so we'll leave it at that. And so, how would we break this guy up?
A over x plus b over x minus 1 plus cx.
So we break, once we have a denominator that's fully factored and we know that the power on top is smaller than the power on the bottom, we start to break it up across the factors in the denominator such that the numerator is a generic numerator that is 1 degree less than the denominator. So the denominator here is a first degree polynomial, so the numerators have to be 0 degree polynomials. If the denominator is a second degree polynomial, the numerator has to be a first degree polynomial. And so what we do is we multiply both sides by the denominator of this guy, so we end up with 2x cubed minus 4x minus 8 is equal to a times, the x's would cancel. In the case of the b, the x minus 1 would cancel. And in the case of the cx plus d, we'll need another line here. The x squared plus 4 would cancel. Okay, how would you proceed from here? How do we find A, B, C, and D? Yeah?
You could have x equals 0 to find a.
You can plug in x equals 0. That will kill this because there's an x and there's an x, so that will kill both of these terms, and you can be able to solve for the a. So if I pick the convenient value x equals 0, 0, 0, here I'd have minus 8 equals a times minus 1 times 4. And this will die and that will die. And so a, I know is going to be what, 2. Okay, what else can we do? Yeah?
Plug in x equals 1 to find b.
You can plug in x equals 1. So on this side, that would just be 2 minus 4, which is minus 2, minus 8, that's just minus 10. That would die, this would die, and here we'll get b times 5, which means that our b is minus 2. Now what? Yeah?
Plug in -1.
Plug in -1, so you're picking just another random number because we can't really kill everything else besides 1. Okay, so plug in a -1, this will be minus 2 plus 4, right? So that will give me plus 2 minus 8, so that's minus 6. -1 here would give me a times minus 2 times 5. Plus, here if I plug in -1, that will give me b times minus 1 times 5. Plug in -1 here, that will give me minus c plus d times minus 1 times minus 2. So here, I actually know already that a is 2, so I can plug that in here. So this is minus 6 is equal to, this would be minus 4 times 5, so that's minus 20. I also know that b is minus 2, so that would give me 10. And here, I would have, this will give me plus 2, so that is 2d minus 2c. So here I would get minus 10, move it over there, I get positive 10. And so this would give me positive 4 is equal to 2d minus 2c. Or in other words, d minus c is equal to 2. You can plug in another number if you want. What x value you want to plug in here? Maybe positive 2 maybe? Something small, or the smallest thing just above that. What will positive 2 give us? I plug in 2 here, that's 8. So that gives us 16 minus 8 minus 8, right? So that's 0. So 0 is equal to a times, I'm plugging in positive 2. So this would be 1. This would be 8. Plus b times positive 2 times 8. Plus 2c plus d times 2. I know that a is 2, so let's plug that in. So this is 0 is equal to 16, b is minus 2. Right, so that's what, minus 32? And I don't really know anything else, but I know that this will be 2d plus 4c. And so what I would get is 16 is equal to 2d plus 4c, or I can divide both sides by 2 here, and that's 8 is equal to d plus 2c. How can I solve for, well, I have this equation here.
You can.
So I also know that d minus c is equal to 2. So if I call this equation 1, call that equation 2, I can say take the top equation minus the bottom equation. Right? So this minus this is 6, d minus d is 0, 2c minus a minus c would give me 3c. This is equation 1 minus equation 2. This would mean that my c is equal to 2. This would mean that d minus 2 is equal to 2, which would mean my d is equal to 4. This means A is 2, B is minus 2, C is 2, and D is 4. And those would be the partial fractions. There are two steps that are really important, which I'll definitely test you on. So it's this step here. Just knowing in generic terms how a larger fraction breaks down to a smaller one. There are times when I don't really want you to waste your time doing algebra. I just want you to know, do you kind of know what this would sort of look like? And so I just might ask you to find the partial fractions, but you don't need to solve for the arbitrary constants. Okay? And so you would leave this as the answer. But in any case, if you have to solve for the arbitrary constants, this is one of the processes you might go through, and this will end up being the answer. So you want to look out for that phrase that says, oh, you don't have to solve for the arbitrary constants, in which case you'll stop here, but otherwise you need to do the full thing. And the variation on the problems can be very different, so there's really no one size fits all. Once you get to this equation, you just kind of do whatever you have to do that's mathematically sound to solve for the variables. And this here we're using method 1, where we're just plugging in x values and getting a bunch of equations, and we can solve for it that way. Because doing method 2 and the multiplying out, it felt like it would be annoying here, so we kind of just went with the plugging in numbers. Any questions? Yeah.
I just want to clarify the basic algebra thing.
Yeah.
For the part B fraction where we had the minus 2, you can't say the whole thing's negative because that's part
You can.
denominator too.
So inside of you could remove the minus here and put the minus here.
Okay.
That
So
is-
it doesn't affect the denominator, right?
No, like a negative sign would only affect 1.
Okay, right.
So basically like a negative sign, you can think of it as like a negative 1 divided by 1, so the top can multiply. You can also think of it as 1 divided by negative 1. So you just apply the negative to either the top or the bottom,
Oh, okay.
but not both.
Mhm.
You can't apply it to both, because if there's a negative on the top and the bottom, it just
Oh,
cancels
yeah,
and you get a positive.
Okay.
So that's this one down. Let's try this one. See if you know how to break that one up. Yeah, some of these can take a while, so that would sort of suggest to you that if on like the test, like I'm not going to give you like 5 problems with partial fractions because they can take a while, especially the interesting problems. But there are things that you should know about how to deal with in general. So, what about that one?
AX plus.
Can we jump into the method here?
Split the denominator into.
Yeah, but remember you always check first that the power on top is smaller than the power on the bottom. The power on the bottom in this case is x to the 4, the power on top is x cubed. So we can start by doing our breakdown. So we have 8x cubed plus 13x over x squared plus 2 squared. How would we break that up?
Eight
What would the denominators be?
x squared plus 2 times.
I mean in the partial fractions, how many denominators do we have?
2.
There are 2 of them.
Yeah, x squared plus 2.
Squared.
Right, so this is a case where you count up to the power. Right, so we have that square, so that's going to break it down. X squared plus 2 we can't really factor further, so we kind of jump into that. So the numerators would be
AX plus B.
ax plus b. And here,
CX plus D.
right, so the numerator is going by the inside factor, right? So the inside factor is a quadratic. Even though technically the denominator here is a 4th degree, the inside factor is what we're looking at when we discover the numerator. And that's sort of just because of how it would break down if we thought of x squared plus 2 as the variable. Okay, and then you can multiply both sides by this denominator, so that would give you 8x cubed plus 13x is equal to ax plus b. Well, you multiply by this, that would be x squared plus 2, plus this would just be cx plus d. Okay, ideas? That should be. It's funny, I'm getting a cold again, and so when I said D, B, it sounded like D, and I wrote down the D. Okay, so that's what we have. What do we do now? Yeah?
Plug in x equals 0.
X equals 0 seems like it would be a nice thing. What do we have left with here? If I plugged in x equals 0, I get 0 on this side. On that side, the A would die, I would have 2B. The C would die, I would just have D. Okay, what else?
I think it might be easiest to like FOIL and then see like which factors.
Yeah, in this case, method 2 seems to sort of be the better way to go here. I could continue with this and plug in 4 things, but no other x value is really going to kill a lot of the guys. Pretty much every other x value I plug in, you're going to have all 4 variables still present, and that's kind of going to be annoying. And since here, it's not going to be crazy hard to multiply out, so I'd probably choose method 2 here. Now it's not that anything is wrong with doing this, we could continue doing that, but I think the other way would be easier. And the more you practice this, the more you'd sort of get a feel for which method you'd want to go for. So what I would kind of do here, when you FOIL this out, you would get ax cubed plus 2ax. Plus bx squared plus 2b plus cx plus d. And then what we do is we group there's only one x cubed, right? How many x squares are there?
One, there's one.
There's only one x squared, that's just bx squared, is that right? How many x's are there? There are 2. So it seems there's a 2a plus c, and those are the x's. So I got rid of the x cubed, I got rid of b squared, I got rid of the x's, and now there's a constant term, that's that 2b plus d. Right? And now this, we already have some good things happening here, because I automatically can see pretty easily what the a value is, right? It has to be 8, right? Because this is an equation. The number of x cubes on this side must be the same as the number of x cubes on that side, and there are 8 x cubes on this side. How many x squares are there on this side?
0.
0. So how many x squares should I have here?
0.
So what does that mean b is?
Yeah,
So that automatically means b equals 0. So that gives me that right away. How many x's I should have? Well, I should have 13. So that means that 2a plus c should be 13. But I already know what a is, so I can figure out the c pretty easily. I also know that the 2b plus d should be equal to what? 0, because there's no constant over here, so there should be no constant over here. So this is automatically 0. So this ends up being a much easier approach. So here I know that my a equals 8. I know that my b equals 0. So this means that 2a plus c equals 13. This would mean that a is 8, so this means that 16 plus c equals 13.
Oh, see.
And so c equals -3 right away. We also know that 2b plus d equals 0. Wait, my b is 0, so the d is 0. So this means that d is 0. And so what does this break up into? Yeah. This means that my 8x cubed plus 13x over x squared plus 2 squared equals, a is 8. That's 8x over x squared plus 2. B is 0. My c is -3. And the d is 0. So those are the two smaller fractions that guy would break up into. And in this case, I think method 2 would be a lot faster than method 1. So basically the idea is after you go through the homework and you do a lot of these problems, you'll sort of get a feel for what method 1 would entail, what method 2 would entail. You'll kind of be able to look into the future. Okay, if I choose method 1, this is how it's going to fall out. If I choose method 2, this is how it's going to fall out. And you can sort of choose what you want to do before. So here it was easier to fall out, combine the like powers of x, and then just look at the coefficients. That was pretty quickly. We could pretty quickly do that here. Let's start this example over here. How do we do that one? Huh? Yeah, the powers are the same. So that doesn't, it means that our partial fractions, trying this breakdown would not work. In fact, I think more than likely if you try to do this breakdown, what will happen is you'll get back exactly the same fraction. It wouldn't actually help you. So you could do long division. There's another step though. These guys are the same and it's not that complicated, so you could also just try try to get the denominator in the top, so I can do x squared, and I can subtract 1 and add 1. This is an option. What's the point of that? Well, now I can break this fraction up into two parts. I can break it into that part and into that part, because we can break a fraction along the numerator. And so I could say this is just x squared. This is just x squared minus 1 over x squared minus 1 plus 1 over x squared minus 1. Or you could have done the long division or the synthetic division, and so you'll have x squared divided by x squared minus 1. X squared to x squared goes 1 time. 1 times this is x squared. 1 times that is minus 1. Subtract that, and you'll end up with 1 as the remainder. X squared to 1 you can't, so that's your remainder. And so then this will again give us 1 plus 1 over the divisor. So you can get to that in two ways. Now that you have that, what can we do here?
Now you can split the fraction, I mean the denominator.
Now we can do partial fractions on this guy. Now there are things that if we want to integrate x squared minus 1, there are 1 over x squared minus 1, there are functions that we could use, but let's just say we want to stick to partial fractions, right? So now, do partial fractions on 1 over x squared minus 1. And so 1 over x squared minus 1 would be equal to, the numerator is 0, the denominator has power 2, the numerator has power 0, the denominator has power 2, so that this can work. So we factor the denominator, which will become 1.
X minus 1.
X minus 1 times x plus 1. By the way, this here is a sum of, it's a product of linear factors with multiplicity 1, so we can actually do our trick, right?
So 80.
So x equals 1 makes this 0, cover that up and plug in x equals 1, you get a half. X equals minus 1 makes this 0, cover that up, plug in minus 1, you get minus a half. And that's your partial fractions right there. So this means that if I start out with x squared over x squared minus 1, this is actually going to be equal to 1 plus this minus that. And if I had to integrate individually, each of those are pretty easy to integrate. Yeah.
Do you mind just repeating one more time how you got the halves for the numerator? The 1 half. Like where'd you plug?
Well, you first split it up into these denominators, okay? Then each denominator, this only works if you have linear factors and they don't have powers, right? So in each one, you figure out the x value that makes that denominator 0. Then you go back to the main fraction, you cover that part up, and you plug in that number.
Okay.
So x equals 1 makes it 0, so I'll cover that up and plug in 1 here. You get 1 over 1 plus 1, which is a half. X equals minus 1 makes this 0, so I go to the main fraction, cover that up, and plug in minus 1. You get minus 1. That's an application of the residue theorem from complex analysis, which in the case of linear factors, it's pretty easy to apply. But in this case, you could also go through the a over this plus b over that, but I think it's a waste of time. Okay, let's see how many of these guys we can get through. So if you see that on a test, what would you do? Panic. No. We're not going to panic.
They're the same degree.
maybe for 2 seconds, and then you recover, and you're okay. Think. What do you do? They're the same degree in the top and the bottom, so you can apply partial fractions right away. Again, another option is always to like complete the square and then do a trig sum, but we always try to avoid trig sum unless it cannot be avoided. But what can we do here? So you kind of have to do either a long division or maybe algebraic manipulation.
You got the numerator?
Yeah, so which I probably do here. I mean, you could go through the long division, but I probably want to try something else here. Because the top is the same, it's already a 4x squared. So what I would do is I probably want to write the minus 3x in terms of minus 4x. I know minus 3x, I can write it as minus 4x plus x, right? So I broke up the minus 3x. The plus 2, I can write it as plus 3 and then minus 1. Plus 2 here I can write as plus 3 and then minus 1. So my 2 I'm breaking up into plus 3 and minus 1. And my minus 3x I'm breaking up into minus 4 and plus x. Now again, this sort of takes practice to see it. If you don't see it, you can always do long division and jump into it. But now this is easily, I can actually break this into 2 fractions. This will just be the integral of 1 plus x minus 1 over this guy. So you can get to here from long division, but if you see that, that's a lot nicer and a lot easier. And what can we do with that one? Ideas? How do we break this up? Does the denominator factor? Does it factor? Okay, well that could be sort of annoying. Let's see if we can do something here. So if it doesn't factor, can we complete the square or something like that? What would the complete square look like here? Wait, that doesn't factor? I didn't choose one that factored. Why would I choose that example? Are we sure it doesn't factor? Let me just check. So this is 4x. I mean, that's one option. So I put the 3 here and the 1 here. That's not going to work. If this, they both have 2.
You get -8.
That's not nice. What can we do then?
Split it up into like 3 integrals, so like integral of 1 dx plus the integral of x over 4x squared minus 4x plus 3. and then minus the integral of 1 over 4x squared minus 1.
Yeah, but how are you dealing with that denominator?
I guess, well, for the second integral, we could like use sub it, and then for the third integral, you have to do a trick sub, I think.
It's not nice, that's, I think I miscopied a number here. Cause here we kind of like have to do like a trick sub or something. Maybe if we complete the square, we'll see something nicer. What would how do I complete the square for this? Well, you have to factor out the 4. And so this would be x minus x. I don't think this is gonna be nice.
Maybe it's meant to be minus 3 up there. Cause I think that would make it work, cause then you could do 2x plus 1 and 2x minus 3. Okay.
Yeah, that does work. I think, yeah, I think I copied the sign wrong. But then that would mean that the numerator would break into sign. Yeah, let's just scrap this example. Because now then that would change what this.
You can factor out a 2x plus 1 then, and then you.
Yeah, and that would have been nicer. That was meant to be a minus. Don't want to waste time recovering that guy. Let's just move on. I'm gonna make sure I change that sign in my notes. Tomorrow's lecture will probably be short. I mean, if time permits, we can probably go over it. The right one. Let's just move on. Ideas for this one?
For root x.
Rewrite root x as, rewrite root x as x to the half. Rewrite the movement.
Okay, and then what?
I mean, we could just factor the denominator right there. Because it's just root x minus 2, root x plus 2.
Could we do that? Sure, now?
Can you do that with, actually? Does that work?
Yeah, but how do you continue? So having the radicals there would be annoying, so you probably want to get rid of them, right? So what would you substitute? So I can do a substitution like u equals radical x. Or in other words, that means u squared is equal to x. So mean that 2u du is equal to dx. And so that would give us the integral. I'll replace all my radical x's with u's. My dx would be replaced by 2u du. And so basically what I end up with is 2 times u squared over u minus 2 times u plus 2. How would we approach that with partial fractions? Can we approach it with partial fractions? What would we do next?
Now do you have the long parts? It's not small enough.
Right, because this, you have to realize that there's a u squared over, this is u squared minus 4 here. So we can kind of split that up by doing, say, a minus 4 plus 4. And so this would be equal to the integral of, well, 2 times the integral of 1 plus 4 over u squared minus 4. This guy now I realize is u minus 2 times u plus 2. So I know that was going to u minus 2, u plus 2. That's a product of linear factors, so I can do our trick. Cover that up, plug in 2, you get 1. Cover this up, plug in minus 2, you get minus 1. So that's actually that guy. That's the partial fractions. So this would be 2 times u plus ln of u minus 2 minus ln of u plus 2. So this is 2 times our u was radical x. So this is radical x plus ln of radical x minus 2 minus ln of radical x plus 2. Kind of running out of time, so let me show you how to start off the others. Even though technically I did enough, so we'll make the partial fractions homework due for tomorrow. So you had something like e to the x over e to the 2x plus 1. How do you approach that? First I would do u equals e to the x, so my du is equal to e to the x dx. That's right here. So the integral would then become 1 over u squared plus 1 times u minus 1. And then this guy you would break up into something over u squared plus 1, u minus 1. So this would be like an AU plus B. This would be like a C. And then you continue. In the case of a cosine x over sine x times sine x minus 1 dx, I would have done u equals sine x. My du would be cosine x dx. And so this guy just becomes 1 over u times u minus 1 du. That one's actually not so bad. That splits up into this type guy. So I plug in u equals 0, I get minus 1. Plug in u equals 1, I get plus 1. Just minus ln of u plus ln of u minus 1. Okay, that one wasn't so bad. I think you guys will know how to continue with that one, so let's move on to this one. We did this by tricks of before, so you can actually compare the methods. Probably what I would do here is something like u squared equals 1 plus x squared, so 2u du would be equal to 2x dx. And so what I would do here is multiply this by x over x. So my integral would look like 1 plus x squared times x dx over x squared. 2's cancel. So basically what would happen then is that this integral would become, this guy would be u, that guy would be u du. X squared is actually going to be u squared minus 1. So this would just become u squared over u squared minus 1, which we did something similar to that. And so that guy will become. And so that'd be u squared minus 1 plus 1, so I end up with the integral of 1 plus 1 over u squared minus 1. Which is 1 plus u minus 1 over u plus 1. So if I plugged in 1, I would get a half. I think we already did this guy. So that would be that. So we can largely do this in our heads for the most part. Well, after a lot of practice. So then this will be the integral of 1. Well, we can integrate that. That's just going to be u plus 1/2 of ln of u minus 1 minus 1/2 ln of u plus 1. And then you plug in your u. So your u was the square root of 1 plus x squared plus 1/2 ln of the square root of 1 plus x squared minus a half ln of the square root of 1 plus x squared plus 1. I think the comparison is a no contest. I mean, you guys remember when we were doing tricks up for that guy? Like here we can just like, you're just writing, you're doing everything in your head. Before it was like crazy. Okay. We'll stop there. Homework for this is due tomorrow. We'll also maybe go over that example that we botched just for extra practice, and we'll move on to approximate integration.